Good morning, dear friends. I'm Saul. Today I'm with a new video of biochemistry course. In this video, we'll see detail about chemistry of lipids. Lipids are the second biomolecules next to carbohydrate. So we'll in detail discuss about these biomolecules. So please don't forget to like and share this video, and let us proceed to the main part of the video. Unit 4 is about chemistry of lipids, and these lipids include fats and oil. Lipids may be defined as compounds which are relatively insoluble in water, but freely soluble in nonpolar organic solvents such as benzene, chloroform, ether, hot alcohol, acetone, and the like. The next point is about classification of lipids. Lipids can be classified as simple lipids, for example, triglyceride or triacylglycerol and wax are type of these lipids, and they are formed from glycerol or alcohol that is esterified with 3 fatty acids. For example, if this is glycerol and it is esterified with 3 fatty acids. Therefore, in simple lipids, 1 glycerol and 3 fatty acids are esterified to make simple lipids. Esterified means the bond that held these two molecules to each other in triglyceride is ester bond. Therefore, simple lipids only glycerol and 3 fatty acids are joined together through this ester bond. The second category of lipids is compound lipids. So in compound lipids, glycerol, fatty acids, and 1 extra or additional molecules are joined together through ester bond. So depending on the extra group, this subclass of lipids are classified as phosphorylated or phospholipids and non-phosphorylated lipids. For example, in phospholipids, 1 glycerol and 2 fatty acids, 1 glycerol, 2 fatty acids, and 1 phosphate molecule are joined together to make phospholipid. So 1 glycerol, 2 fatty acids, and 1 phosphate molecule are joined through ester bond to make this phospholipid. The third category of lipids are derived lipids. These are compounds which are derived from lipids or they are precursors of lipids. That means these derived lipids are formed or they are derived from hydrolysis of lipids, or they are used for the formation of lipids. So they can be used as a precursors for the formation of lipids. Otherwise, they are not directly lipids. For example, fatty acids, which are part of lipids and they are used to make lipids, or even they are the result of hydrolysis of lipid molecules. Still, steroids and prostaglandins are also derivative lipids. The fourth category of lipids is lipids which are complexed with other compounds. For example, lipids or lipoproteins, as well as glycoproteins. In lipoproteins, lipid plus protein are joined together. They are complexed to each other to make this molecule. In glycolipids, carbohydrates and lipids are complex to each other, and they make these glycolipids. So these are lipids that are complexed with other compounds. Lipids are esters of fatty acid and alcohol or glycerol. So here I'm going to show you how these ester bonds are formed between glycerol and fatty acid. So first let us see structure of these molecules, structure of glycerol and the structure of fatty acids. Glycerol has these 3 carbon atoms, and it has also these OH groups which are attached to each of these carbon atoms. The fatty acids contain the carboxylic acid group part as well as the hydrocarbon chain part. So the bond is formed between, that means the ester bond is formed between each of carbon atoms of glycerol and the carbon atom of the carboxylic acid group part of the fatty acids. So first this glycerol loses this hydrogen. This hydrogen is detached from oxygen. They are detached from oxygen, and the OH groups are removed or detached from carboxylic acid part of the fatty acids for 3 fatty acids. These molecules are detached. Now this oxygen now join the 2 carbon together. These oxygens join the 2 carbon together. This carbon. As a result, here 3 hydrogen atoms are lost from glycerol, and the 3 OH groups are lost from fatty acids. Therefore, as a result, 3 water molecules are formed. So, from 1 glycerol and 3 fatty acids, there is 1 triglyceride and 3 water molecules are formed, and the bond that link the glycerol and 3 fatty acids is ester bond. This is ester bonds. The following are main functions of lipids. For example, they are used for storage of energy. For example, this triglyceride is used to store chemical energy, and lipids can be used as structural components of biological membranes. For example, cell membrane is made up of mainly this phospholipid, and it also has this cholesterol. Therefore, phospholipid and cholesterol are components of cell membrane. Lipids can be used as metabolic regulators. For example, steroid hormones and prostaglandins can be used as metabolic regulators. Still, lipids can be used as surfactants, detergents, as well as they can be used as emulsifying agents. Lipid can act as electric insulator in neurons. For example, myelin sheath is covered or insulate the neuron, and it helps us not to link out of this electrical message in neurons. Still, lipids provide insulation against external change in temperature. Whenever the external temperature is changed, the body temperature prevents the heat loss, especially in cold environmental condition, by these lipids, especially subcutaneous fat, prevent heat loss from the body in cold environmental condition. Still, lipids can be used as protector internal body from damage. Many internal body organisms are protected by lipids from physical damage. Still, lipids can be used as absorption of fat-soluble vitamins. These fat-soluble vitamins are absorbed in the lipids, and lipids can improve taste and palatability of the our food. So these are some important or main functions of lipids. What are the dietary sources of lipids? The chief dietary sources of lipids in human being include animal source as well as vegetable source. Examples for animal source include dairy products like milk, butter, or ghee, as well as this meat, fish, pork, and egg also contain lipids. Vegetable source, various cooking oil such as sunflower oil, groundnut oil, cottonseed oil, as well as mustard seed oil. These all are from vegetable source. These vegetable lipids are superior to animal fats because of two things. First, they contain more unsaturated fatty acids because lipids are made up of glycerol and fatty acids. So fatty acids in vegetable lipids contain double bonds. Their fatty acids contain double bonds in their hydrocarbon chain. Therefore, they contain polyunsaturated fatty acids. But lipids from animal source contain saturated fatty acids. This is one difference. Second, lipids from vegetable source are less likely to go this rancid. Rancid means change it into sour taste. In Amharic, komdata. So, because of the presence of antioxidants, they are less likely to go to this rancid or sour in taste or komdata in Amharic. Therefore, because of at least these two things, vegetable lipids are more preferable than animal source. The next point is about digestion and absorption of lipids. Once food containing lipids are digested, then after the end products are absorbed. However, digestion of fat or digestion of lipids has a special problem because, as you know, lipids are insoluble in water, but enzymes which catalyze digestion of lipids is soluble in aqueous media or in the water because all enzymes are protein, so these lipolytic enzymes are protein, so they can be dissolved in water. So if the substrate, that means the lipid and the enzymes are not contacted to each other, the digestion reaction is difficult. Therefore, our body solves this problem by emulsification process of this fat or lipids. This emulsification process is carried out by bile salts. Therefore, in emulsification, these larger fat particles or larger oil globules are broken down into smaller fine particles. Then these smaller fine particles can easily be hydrolyzed by the help of these lipolytic enzymes. So this problem is solved by emulsification actions of bile salts. Digestion of lipids in the mouth. This digestion includes physical digestion and chemical digestion. So our focus is on chemical digestion. It was believed that little or no fat digestion takes place in the mouth. As you know, physically, any food is digested in our mouth by the chewing actions of our teeth. However, it was believed that there is no or little digestion of fat chemically. However, recently this lingual lipase is detected, which are produced by dorsal surface of the tongue by Eber's glands. So, by the help of by the catalytic actions of this lingual lipase, lipids are digested in the mouth chemically. The pH value of lingual lipase is from 2 to 7.5. However, the optimum pH is from 4 to 4.5. Optimum pH is where maximum rate of reaction is occurred. The next organ in which food is digested is stomach. Therefore, digestion of lipids in the stomach. This lingual lipase or triacylglycerol lipase from the mouth directly enter into the stomach along with the food, and its activity continues in the stomach too. Reason the optimum pH of this stomach is 2.5 to 5. This pH value is also suitable for the catalytic actions of this lingual lipase. Therefore, because the optimum pH of this lingual lipase is also from 4 to 4.5. Therefore, this lingual lipase is active in the mouth as well as it is active in the stomach. Second, this lingual lipase acts on short chains of triglycerides because these triglycerides are made up of glycerol and fatty acids. Therefore, if the triglycerides contain short chains of fatty acids, so they are targeted by this lingual lipase. And the next, lingual lipase is more significant in newborn infants. The other lipase type is gastric lipase, which is acid stable and with an optimum pH of 5.4. Around 13% of triglyceride digestion of triglyceride occurs in the stomach because this food stays for 2 to 3 hours in the stomach. So relatively, the food stays in the stomach longer time. So around 13% of digestions of triglyceride occurs in the stomach. The role of fat in the stomach. Fats play one important role in the stomach in that they delay the rate of emptying of the stomach because introgastral hormone is produced when fatty foods are present in the stomach. This, the introgastral hormone, slows down stomach emptying by reducing the amount of acid produced. Because when the acid production increases, the opening between the stomach and the small intestine increases. But in the presence of fatty food, there is production of introgastral hormone, which reduces the production of acids in the stomach, and the size of the opening between the stomach and the small intestine is reduced. Therefore, the food stays longer time in the stomach. Therefore, fats have high satiety value. The second point is about digestion of lipids in intestine. Once the food is digested in the stomach, then it passes to intestine. So the major site of fat digestion is small intestine. This is because of the presence of two major molecules. One is the presence of powerful lipase or stepsin in the pancreatic juice, and the presence of bile salt, which acts as emulsifying agent for fats. So, due to the presence of powerful lipase as well as the presence of bile salts, this small intestine is a major site for fat digestion. This pancreatic juice contains a number of lipolytic enzymes. These lipolytic enzymes include pancreatic lipase or stepsin, which hydrolyze short chain and long chain fatty acid containing triglycerides. Or in short, this pancreatic lipase can hydrolyze these triglycerides. And this pancreatic lipase, or step C, is an esterase with an optimum pH of 6. The second lipolytic enzyme is phospholipase A2, or it is known as lystinase. This lystinase hydrolyzes this phospholipase, or it is phospholipase can be hydrolyzed by phospholipase. The third one is cholesterol esterase, which hydrolyzes the cholesterol. The role of bile salts and this colipase. Bile salts are required for the proper functioning of this pancreatic lipase, because these bile salts must emulsify the triglycerides into smaller particles. Then after this pancreatic lipase act upon and hydrolyze it. But this pancreatic lipase first combined with colipase. These colipase are small protein molecules. They are 2 in number, and they are combined with pancreatic lipase. This helps the enzyme in 2 ways. First, the activity of pancreatic lipase is enhanced by the combination of this colipase at intestinal pH. Second, this combination, the combination of pancreatic lipase with colipase, protects the enzyme against inhibitory effect of bile salts. If pancreatic lipase acts alone on the hydrolysis of triglycerides, these bile salts inhibit its activity. So to protect from inhibitory effect of bile salts, this pancreatic lipase must be combined with colipase. Second, still these bile salts will denature the surface of this pancreatic lipase. Therefore, this pancreatic lipase must be combined with colipase to be saved from or against surface denaturation of bile salts. Bile salts, or known as sodium glycolate and sodium thiocolate, also help in emulsification of fats. They emulsify fat into fat droplets. The emulsification or the dispersion increases surface area and lowers the surface tension of the fat. Then after, it enhances the activities of pancreatic lipase. This is, for example, this is a fat particle, which is emulsified by the bile salts into smaller particles. Large molecule is broken down physically into smaller particles. Then after, it is easy to be hydrolyzed by the pancreatic lipase. Therefore, bile salts enhance the activities of pancreatic lipase by breaking down physically the large particles of fat into smaller particles. The process is known as emulsification. The role of calcium ion in lipid digestion. Calcium ion plays an important role in the digestion of lipids, because in the presence of calcium ion in the intestine, free fatty acids, which are derived from lipids, are immediately precipitated out as soaps or insoluble calcium soaps. So this enhances the accessibility of lipase with emulsified lipids. So in general, this calcium ion facilitates lipase action or lipase activity. Mode of action of pancreatic lipase. As you know, this complete hydrolysis of fat or triglyceride produce free glycerol and 3 fatty acids, because this glycerol is attached with 3 fatty acids to produce triglyceride. Therefore, in hydrolysis of triglyceride, 3 fatty acid and glycerol are formed. However, this pancreatic lipase is specific for hydrolysis of primary ester linkages. These primary ester linkages are formed at the alpha carbon, the second alpha carbon, and this is beta carbon. The two carbons which are found in the tip are considered as alpha carbons or primary carbons. Therefore, this bond that held fatty acids with glycerol at the first carbon and as the second carbon are known as primary ester linkage or primary ester bonds. So this pancreatic lipase is specifically a break or hydrolyze ester bonds at the primary position, but not at the beta position or at the second position. Therefore, this process, the hydrolysis of triglyceride by pancreatic lipase, is more or less slow rate of reaction. To make more clear this digestion of triglyceride molecule by pancreatic lipase, this is a triglyceride molecule which is made of one glycerol in the 3 fatty acids that are attached through ester bond. But the ester bond is found at 2 alpha carbons. This is first alpha carbon and the other alpha carbon. In between these two, there is beta carbon, and the bond is also known as beta ester linkage or ester bond. So when this molecule is hydrolyzed by pancreatic lipase, the first fatty acid is lost, and then OH group is come in this position. So the molecule is alpha beta diglyceride, because one fatty acid is lost from triglyceride, therefore diglyceride is left. And when the second pancreatic lipase comes and remove fatty acid from another alpha carbon, so another OH group is attached to its position. So now what is left? Beta monoglyceride, because beta is the second position. This is the second position. So one fatty acid is left, and now pancreatic lipase doesn't act upon beta carbon position. It doesn't hydrolyze the ester bond at beta position. So this beta monoglyceride must be isomerized, and it must shift its fatty acid into one of the alpha position. Therefore, this fatty acid is shifted from beta position to one of alpha position. Now, this pancreatic lipase come and remove another fatty acid from this alpha carbon. Now, glycerol and the 3 fatty acids are produced. However, recently scientists have found an enzyme that hydrolyzes fatty acid esterified at beta position or at the second position of the triglycerides, and this enzyme is found in the rat pancreatic juice, not in human pancreatic juice. And this enzyme is not pancreatic lipase, rather it is known as estroesterase hydrolase. Estroester hydrolase, the name of this enzyme that hydrolyze fatty acids at beta positions of triglyceride. These bile salts, salps, which are precipitated fatty acids with calcium ion and bicarbonate, which are found in the pancreatic and intestinal juice, collect many fatty acids, mono and diglycerols, listings, which are mixtures of different fats, and cholesterol, and other to form water-soluble molecular aggregates known as mixed micelle. These all molecules are collected and mixed to each other and aggregate to each other to make this mixed micelle. So these mixed micelle are much smaller than fat droplets, and they are water soluble, as well as they are absorbed mainly from duodenum and the jejunum. So these molecules, mixed micelle, help us absorption of fats in the small intestine. Absorption of lipids. Once digestion is over, then the end products are absorbed to the target cell to be used for a number of functions. This is absorption of long-chain fatty acids. Long-chain fatty acids with a chain length more than 14 carbon atoms are absorbed into lymph, not into the blood. They are absorbed to the lymph, not into the blood. The micelles are aligned at the microvillous surface of jejunum mucosal cell. In the micelles, there are long chains of fatty acids. So, in the mucosal cell, these long chains of fatty acids are esterified to form new triglycerides. This type of triglycerides are not dietary triglycerides, rather they are formed in the intestinal mucosal cell. So these long chains of fatty acids are used to form a new triglycerides in the intestinal mucosal cell. However, bile salts are left behind, which are mostly reabsorbed from ileum and returned back into liver, because they are originated from liver and they are returned back to their original site. Absorption of short chain and medium chain fatty acids. These short chain fatty acids and medium chain fatty acids with a carbon atom of less than 14 are not esterified into new triglycerides. Rather, they are directly enter into blood vessels and then into hepatic portal vein. Then finally, they are taken into liver, where they are immediately utilized for energy production. So their production is relatively fast, or they are rapidly absorbed than that of long chains of fatty acids. Absorption of glycerol. Free glycerol are absorbed from intestinal lamina directly enter into bloodstream like that of short and medium chains of fatty acids. So there is no free glycerol is available for the esterification purpose. But the cells convert glucose into glycerol to synthesize triglycerides from long chains of fatty acids. Otherwise, the glycerol, which is formed from dietary triglyceride, is taken into bloodstream, and it is not available for esterification purpose. Thank you for watching, and I will come back soon with the second part of this chapter, and see you.